Have you ever really stopped to think about why things move the way they do? I mean, from a planet going around the sun to just tossing a ball across the yard? It turns out everything, and I mean everything, follows a hidden set of rules. And these aren't just for scientists in a lab, they're the invisible architecture of our everyday world. So let's dive in and uncover these secret rules of motion together.
Think about this for a second. We've all been there, right? You're on a bus, it hits the brakes suddenly, and your whole body lurches forward. Or you know instinctively that trying to push a huge truck is way harder than giving a little kid's bicycle a shove. Well, these feelings aren't random. They are you, personally, experiencing the fundamental laws of motion. Today, we're going to pull back the curtain and see exactly why this stuff happens.
Okay, so before we can really get into the rules themselves, we need to learn the language. Physicists have a super precise way of talking about movement, and if we could just get these basic terms down, it's going to unlock everything else.
First up, let's talk about a difference that seems small but is actually huge. It's the difference between distance and displacement. So imagine you walk all the way around a city block and end up right back where you started. The distance you walked might be, say, a whole kilometer, but your displacement, which is just the straight line from your start point to your end point, is a big fat zero. See, distance is just a number, but displacement has a number and a direction. That makes it what we call a vector.
And that idea of direction brings us straight to velocity. Now, velocity is not just speed. Saying a car is driving at 100 kilometers per hour, well, that's its speed. But saying it's going 100 kilometers per hour north, now that's its velocity. That direction part is absolutely crucial, because if you change your direction, even if your speed stays the same, you've changed your velocity.
Right, and any change in velocity, any change at all, is called acceleration. We usually think this just means hitting the gas pedal and going faster. But in physics, hitting the brakes is also acceleration. We just happen to call it deceleration. Heck, even just turning a corner at a perfectly steady speed is a form of acceleration, because your direction, and therefore your velocity, is constantly changing.
All right, now that we've got the lingo down, let's get to the first big fundamental rule. I like to call it the law of laziness, but you might know it by its official name, inertia. It's basically an object's built-in stubbornness.
The main idea was laid out perfectly by Sir Isaac Newton in his first law of motion. All it's really saying is that things like to keep on doing what they're already doing. You know, if something's just sitting there, it wants to stay sitting there. If it's moving, it wants to keep moving in a nice straight line at the same speed. It's lazy. So this resistance to change, this inertia, is tied directly to an object's mass, how much stuff it's made of. The more mass something has, the more inertia it has. This is exactly why it's so much harder to get a big, heavy truck moving than it is to push a lightweight bicycle. The truck is just way more stubborn.
And you see this principle at play everywhere. When that bus stops short, your body wants to keep moving forward because of its inertia. That's the lurch you feel. When you shake a bottle of chili sauce to get it out, the sauce's inertia is what's making it want to stay put inside the bottle. These aren't all different things. It's the same exact principle showing up over and over again.
So if inertia is this deep-seated resistance to change, then what's the thing that actually causes a change? What overcomes that laziness? Well, that brings us right to our next big ideas: force and momentum. And here it is, maybe the most famous equation in all of science, F equals ma. This is Newton's second law. It tells us that if you want to make some amount of mass, m, accelerate, a, you have to apply a force, F. Simple as that. A bigger mass, or a bigger acceleration, is going to require a bigger force. This is the engine that drives all change in motion. Now, when an object with mass is on the move, it has this quality we call momentum. And a really good way to think about it is its unstoppability. It's just its mass times its velocity. So a huge, slow-moving oil tanker can have an incredible amount of momentum, and so can a tiny, super-fast bullet. The point is, both of them are very, very hard to stop. But here's the really amazing thing about momentum. It's conserved. In any collision, think about a cue ball smashing into a rack of billiard balls. The total amount of momentum in that system right before the crash is exactly the same as the total momentum right after. Sure, it gets shuffled around between all the different balls, but none of it is ever lost. It's like the universe keeps a perfectly balanced checkbook. So, all this talk about collisions brings us to a really practical and important topic: impact. It turns out it's not just about how much force is involved in a crash, but how that force gets delivered over time. And this is the key to everything from car safety to playing sports. The force you actually feel during a collision is what we call the impulsive force. And the key thing to get here is the relationship between time and force. For the same change in momentum, if the impact happens in a really short amount of time, you get a massive damaging force. But if you can stretch that impact time out, the force becomes much smaller and way more manageable.
This is the life-saving physics behind a car's crumple zone. The whole front of the car is actually designed to fold up and collapse in an accident. Now, that might just look like destruction, but it's actually an incredibly clever design that increases the time it takes for the car to come to a full stop. By stretching out that impact time, it drastically reduces the peak force that gets transferred to you, the passenger. It's literally physics acting as a bodyguard.
Okay, for our last section, let's clear up one of the most common points of confusion in all of physics, the difference between mass and weight. Believe me, they are not the same thing, and it all has to do with that force that keeps our feet planted firmly on the ground.
The difference is actually pretty simple, but it's profound. Mass is just the amount of matter, the amount of stuff in an object. It's a constant. It doesn't matter where you go in the universe, your mass is your mass. Weight, on the other hand, is a force. Specifically, it's the force of gravity pulling on your mass. And since gravity is different in different places, your weight changes.
This table just makes it crystal clear. Let's take an astronaut who has a mass of 70 kilograms right here on Earth. They travel all the way to the moon, and they still have a mass of 70 kilograms. The amount of astronaut stuff hasn't changed one bit. But look at their weight. On Earth, gravity pulls on them with a force of 687 newtons. But on the moon, where gravity is way weaker, their weight plummets to just 113 newtons. Same person, same mass, but a completely different weight.
So, from the sheer stubbornness of inertia to the life-saving genius of a crumple zone, these aren't just equations you find in a textbook. They're the secret rules that are running every single movement happening all around you all the time. Now that you know them, the real question is, what invisible forces are you going to notice today?